Welcome back. In the previous video, we covered feedback linearization for addressing motion constraints and how we can implement our trajectories with the dynamics of the system. I would like to do a Matlab example to make things more clear. So I would like to do that example for the non-holonomic mobile robot example that I covered previously. So if you remember, we had the motion of the mobile robot is represented by these 5 differential equations. Px and Py denotes the position or Cartesian position of the vehicle. Q was the tangential velocity, theta is the orientation, and F and T were our force and torque control inputs. And to avoid nonlinear, non-holonomic control synthesis, we choose F and T like this, and this allowed us to linearize the system. And if you remember, we end up having hand positions h x dot dot to be the ux. Ux is our virtual control for x-axis, and we had hy dot equals to uy motion for the linearized motion for the y axis. So instead of controlling px and py, we are controlling hx and hy. And remember, this distance was represented L multiplied by cosine and sine terms. So this L should be small enough such that your robot should feel like you are actually approximately controlling px and py. So that's why we need to choose L to be small. Here are the equations, hx px plus L, and here it is. You can start, for example, you can choose it to be 1, 0.5, you can explore. And finally, for the linearized hand coordinates, I mentioned at the end of the video, at the end of this non-holonomic mobile robot example, you can use these type of control signals or its variants with alpha and beta to be positive. Let's jump to the Matlab code. We have some, I'm going to show some pieces, and if you would like to code it yourself, you start from here, then this is the second part of the code, and you can proceed like this. Initialization, we are clearing everything and closing all the figures. Total simulation time is 12 seconds because if you remember on the waypoints video, we curve fitted up to 12 seconds. I am going to discretize continuous time robot dynamics. So this is the first order Euler method discretization sampling. I am choosing all initial conditions to be 0. I will start with alpha and beta being 2 and 1 for the controller, both for ux and uy, virtual control signals. I am choosing mass as the 5 kilograms, inertia to be 10, and L to be 0.25. All right, the second part of the code is motion planning and least squares. We are finding the analytical solution to the least squares problem. This is coming from the motion planning with waypoints video, in that I choose non-parametric radial basis function neural network that is between these radial basis functions are changing from 0 to 12 to cover this independent variable time. And then we are basically finding V1 by multiplying by x. This is the weight that we are going to use for the x command, cx. And so for cy, we are going to use v2 weight, which uses the data points y. Okay. Then simulation starts from t to 0 to final time. These are the commands. I am generating cx and cy by multiplying w1 and w2 transpose with these radial basis functions because I use them for curve fitting. So we have the commands. By the way, I should mention, if you, for example, use the variant of the control signal I showed in the previous video that will include cx dot or cx dot dot, you need to also define here, use the time derivatives of cx and cy. not a hard thing to do. I am skipping that part. I am not going to use cx dot and cy dot, but you can. Here is the feedback linearization process. I defined basically the hand coordinates. I am taking the derivative of the hand coordinates because I need in the control. Then I define the control signal alpha multiplied by hand coordinate minus cx, and the velocity. This is the hx, and here's the hx dot. Same for uy. And I am continuing to the feedback linearization, defining the rotation matrix. This is the force-torque relationship. Basically, it should be this relationship here. The first part plus the ml portion of it. And this way, you will arrive, the first input of this, first entry of this matrix will be your force input, actual control signal. The second entry will be the torque input. Here is the system dynamics that I define, such that I am applying, I am designing virtual control inputs, but applying, of course, the actual force and torque inputs to the system. And this is the pxpy discretized version, right? That's why I am using all dt here, first order Euler method. And final step is storing the data that you see here and also plotting the figures. I am not going to dive into detail. You can pause the video or take the screenshot to use. This is regular 3D and 2D figures. All right, so let's start with alpha equals to 2 and beta equals to 1 case. So robot starts from here. Basically, waypoints are represented by these red dots. This black curve represents the cx, cy. I am basically sketching this cx versus cy. And blue trajectory is the actual px and py of the vehicle, motion of the vehicle. Now, for alpha to be 2 and 1, as you see, it is not bad, but we are a little bit away from the trajectory. And if you are more away from the trajectory, the problems might happen, like hitting the this target. So you always would like to stay sufficiently close to the trajectory. For this, I am basically increasing alpha and beta from 2.1 to 4.2. Now this is a nice trajectory following. Close enough, you are past blue trajectory. Actual motion of the vehicle passes through these waypoints. You can increase further, for example, 8 and 4. These are not high gains. And we are beautifully, basically, it is a beautiful result. We very closely follow the black cx and cy trajectory. So, this non-holonomic mobile robot follows this trajectory very closely. Now, you may ask why we never reach to the last waypoint. Actually, for this purpose, I would like to show this 3D plot time. Again, I would like to use the same example that I used at the beginning of the previous video. Let's say you are driving a car, you hit the gas, right? You hit the gas, but your car will speed up after, it will take some time. If you want your car to go 60 miles per hour, reaching to 60 miles will take some time, depending on your engine, so on and so forth, mass of the vehicle. So this is exactly the phenomena that you have. You would like to track this cx, cy commands, but it takes some time because of the dynamics of the your vehicle, right? If you look at here, the command is here, and it follows the command with some time. So if you simply take it here, in order to reach to the same position, there is I will see from maybe less than a second difference here. So if you then remember, I run this video up to 12 seconds. For example, if you code it yourself and run up to 12.5 seconds, you will see that you have a less than a second gap. Your blue curve will also reach to this target. And this is how you implement basically waypoint motion planning, or you can do the same thing with A star. You basically generate your trajectory, then your inner loop control architecture, so-called the feedback control, indeed makes the dynamics of that vehicle follow the desired commands. All right, take care.